Okay, Chapter 5, Section 5, the fundamental theorem of calculus. Okay, so the definite integral of a function f on an interval from a to b is a number corresponding to the area between the graph of f and the x-axis from x equals to a to x equals to b. The indefinite integral of a function is a family of antiderivatives. This section outlines the connection between the two integrals. To see the connection between the two integrals, let's consider this example. Suppose that the daily cost for a manufacturing firm is described by this equation, C of x equals to 180x plus 200, where x is a value between 0 and 20. Okay, so there is a fixed cost of 200, and then there is an additional cost per unit of 180. So we can see a graph of that equation would look like this, where it's a straight line with a slope of 180, and it crosses the vertical axes at 0, 200, right? At 0 units, there's still a cost of 200. 1 unit will cost you 380. 2 units will cost you twice 180, which is 360, plus 200 gets you to 560, and so on and so forth. So here is that line right there. So as the number of units increase, we also see that the cost steadily increases at a constant rate of $180 for each additional unit. Okay, so now suppose we are asked to determine or think about the change in cost as the production increased from x equals to 5 units to x equals to 10 units. What is the change equal to? Okay, the change in the cost as we go from 5 units to 10 units. So on here, at least pictorially see that we go from 5 units to 10 units. Okay, so if we evaluate our function at x equals to 5, put in a 5 in here, you figure out what the cost was at 5, put in a 10 in here, put in a 10 in there, figure out what the cost is at 10, and then if we subtract them, we'll get our answer. So the work looks like this. So if we evaluate our function, c of 10, we get 180 times 10 plus 200. And then if we evaluate our function at 5, c of 5 is going to give you this result. So this is our c of 10, whereas this is our c of 5. Okay, and then we subtract them and we'll end up with $900. Pictorial here on the graph, we see that the cost function is this straight line. So if we evaluate our function at 5, evaluate it at 10, and subtract them, we'll see that the height change, the difference here, corresponds to $900. Okay, so the cost will change by $900, by a quantity of $900, if we go from producing 5 units to producing 10 units. Okay, now let's think about the marginal cost. So given that the cost function is equal to 180x plus 200, we know that the derivative of this function, so ddx of the cost function, is equal to ddx of the 180x plus 200, which then gives me that c prime of x is equal to 180. In other words, the marginal cost of the function c prime of x is equal to 180. Let's think about the graph of that guy now. So if we graph this, well, this is just going to be a constant line. Okay, so the original function is c of x, the cost function. And then after taking the derivative, we see that the marginal cost function is this one, c prime of x. So now if we graph c prime of x, it's a nice boring graph. It's just this straight line, right? It's just a constant. If this was the x and y Cartesian coordinate system, then we would just graph this as y equals to 180. Okay, so now what we want to do is think about the area that's underneath this new graph between 5 and 10. So we're going to come over here and focus on the area between this number and this number on underneath the graph of the first derivative function. It'll look a little like this. Okay, so that area, this area in blue underneath this function, is equal to the base, which is 10 minus 5, that's this base, times the height, and well, the height is 180, it's always 180. And if we multiply those two together, we get 900. So this area here equals 900. Notice that this, when we were doing it this way, this right here is exactly the same as this right here. The same calculation, 180 times 10 minus 5. So notice that the 180 times 10 minus 5 is equal to the area between the graph of c prime of x and the x-axis from 5 to 10. That would be this area, is equal to this over here when we were doing this calculation, which means it's equal to this. So this is how we connect them. We want to state that the c of 10 minus c of 5 is equal to the integral from 5 to 10 on the function c prime of x. In other words, the change in cost from x equals to 5 to x equals to 10 is equal to the area between the marginal cost function and the x-axis from x equals to 5 to x equals to 10. So this is what we really want to take away from this example, this little statement here. So notice the connections between the two. Here we're talking about the cost function, whereas here we're talking about the derivative of the cost function. Remember, 180 is just c prime of x. So we're integrating c prime of x. Here we're evaluating capital C, the underlying function. And so if we evaluate our function, our cost function at 10 minus evaluating our cost function at 5, it's equal to integrating the first derivative function and evaluating it between 5 and 10. Good. So that's what we really want to take out of this. Let's look at one more example. Now suppose a company has a cost function that's a little bit more complicated. Let's say it's equal to this. C of x equals to negative 7.5x squared plus 305x plus 625. So part A, graph C of x for x between 0 and 20, and then calculate the change in cost as x changes from 5 units to 10 units, and indicate that change in the cost on the graph. Okay, so when we produce 0 units, when x equals to 0, we see that there's still a fixed cost of $625. When x is equal to 1 unit, 1 squared will be minus 7.5. And then 1 would be 305. So at 1, we know that we would add these two to make it 630, 930, and then subtract off 7.5, which would make it 922.5. Okay, and then we can find other values that way. So let's just use technology to graph this. I can tell it's going to be a quadratic, so it's going to be some sort of a parabola. Opens down because this leading term is negative. But then just using technology, this is what the graph looks like. So here's our graph. It seems to be climbing. That's an upside down parabola. It reaches some maximum at the vertex, and then it's going to come back down. But we're only interested in the region between 0 and up to 20. So if we look at where 5 is, 1, 2, 3, 4, 5. So 5 is around there somewhere. If we trace it up, we'll end up with some value, say over there. And then 6, 7, 8, 9, 10 is over here. So if we race up and trace it up to there, it would be somewhere around there. So if we can figure out the change that occurs in the cost, that's what they're interested in here. So graph it, calculate the change in cost as X changes from producing 5 units to 10 units. Okay, so we need to figure out the value of C of 10 and then the value of C of 5 and then subtract the two. So C of 10 will be, we can use this equation here to figure it out. 7.5 times 10 squared plus 305 times 10, oh, there's a 10 there, plus 625. And just to put them in color, let's put them in blue. So this is evaluating it at 10, 10, and 10, so we can get a result from there. And then also we can figure out C of 5 with the same formula. So there's a 5 there, a 5 there, and a 5 there. Okay, and then on the graph, it would look like this. Okay, so C of 5 reaches up to here. It looks like it's going to be 1,000. So this calculation here leads to $1,962.50. Whereas this calculation, when we evaluate it at 10, it goes all the way up to there, and that becomes 2,925. If we subtract this number minus this number, we arrive at the difference, which is $962.50. Okay, so the change in cost when you go from producing 5 units to 10 units results in this. Let's highlight the whole thing. Okay, so like before, now let's think about the marginal change. So if we want the marginal cost, then that's the derivative of this cost function. So we have the cost function, C of x is equal to negative 7.5x squared plus 305 x plus 625. We know that when we want to take the derivative with respect to x of the C of x function, that's taking the derivative with respect to x on this polynomial function. So that means that C prime of x is equal to negative 7.5 times 2 x to the first power plus 305, which means that C prime of x is equal to negative 15x plus 305. So the first derivative of the cost function equals to negative 15x plus 305. And the first derivative of the cost function is better known as the marginal cost function. Okay, so C prime of x is equal to negative 15x plus 305, and that's where x ranges between 0 and 20. So just like before, now let's think about graphing this. So let's find the graph of this. It's going to be a linear equation, of course, with a negative slope, negative 15 slope, and a y-intercept axis, or a vertical intercept point of 0, 305, right? If we let the input value be 0, the output is still going to be 305. So this is what the graph looks like. Okay, so here is the graph of C prime x. We know it's a straight line. It's a linear equation with a slope of negative 15, and it crosses the vertical axis at 0, 305. So we know that this point here, that point should be the point 0, 305. Should be that point right there. And again, just like before, we're interested in figuring out the area underneath this function between 5, so between 5 and 10. We want to find the area underneath there, so that should look like this. So we're interested in finding this area right here. Okay, so I know I'm going to need the value of that point, and I'm going to need the value of that point. So let's figure them out. Remember, our function is c prime of x, so I'm going to need to figure out what is c prime of x when we plug in a 5. So it'll be blank minus 15 blank plus 305. And then I'll also need to figure out c prime of blank minus 15 blank plus 305. So one of them will be when we evaluate this at 5. So 5 there, 5 there. And the other one will be when we evaluate this at 10. So 10 there and 10 there. Okay, so if we do a little bit of calculating, we get that this should be 230, whereas this is equal to 115. Okay, so next we want to find this area here. To find this area, I'm going to think about breaking this up into 2 regions. So let's insert a line here that goes from there and comes straight across to there. So that now I have a triangle region and a big rectangle region. That helps me break this up into 2 simple geometric shapes. We know that the area of a triangle is equal to 1/2 base times height. 1/2 times the base times the height. So the entire area is going to be equal to the area of the triangle plus the square, well, the rectangle. So the triangle will be 1/2 base times height. 1/2. In fact, let me zoom into here for a little bit. One half times the base times the height plus the rectangle, which is just going to be length times width. Okay, so this is going to be equal to 1/2. Now the base is going to be this distance, which is 10 minus 5. 10 minus 5. And that is the same base for both the triangle, as well as it's going to be one of the sides of our rectangle. So looking at the triangle, I'm going to consider this as my base right here. So here is my base. And then my height is going to be just the distance from there to there. So what I need to do is subtract this value from that value. Right, so right here, from there to there, that's my height of just the triangle. And I'll be able to find it by evaluating this point, which would be the C sub 5, right? Or the height from 5 up to there, that should be that height. Okay, let's be clear. Let's say this whole height there is C sub 5, whereas this height here is C sub 10. Good. Okay, so then if I do, I'm just going to put it in the same order. It'll be so this will be the 230 minus the 115. and I automatically put it in an order so that I know that I get a positive answer, because an area is a positive thing. Okay, plus now the rectangle, okay, well, one side of it is going to be the 10 minus 5. That gets me this part of it down here, one side of the rectangle. Whereas the other side of the rectangle is going to be this, which is the C of 10, which is the smaller value, the 115. Right? This C of 10, this was 115. Whereas this C of 5, this one was the 230. Okay, I'm going to factor out the both this common term here from both of them. And I'm going to force a 1/2 out of this as well. So I'm going to factor it out. And I'm running out of room here. So this will be 1/2. This will be 1/2, 10 minus 5. And then I factor it out. So 1/2, 10 minus 5 times, and then this term would make it 230 minus 115. Plus, okay, well, we factored out the 10 minus 5, but there wasn't a half here. So if we wanted to factor out a 1/2, I could have introduced the 1/2 by saying, let's just toss it in there, 1/2. But then I got to balance it out by throwing in an extra 2. So 1/2 times 2 becomes 1. I haven't changed anything, but now I can factor out the 1/2, which means that there's a 2 remaining. Good. Times 115. Okay, so this just simplifies as following. The area then becomes equal to 1/2, 10 minus 5 times 230 plus 115. And after a little bit of work, we see that that area is going to be equal to 962.50. Okay, we get the exact same answer that we got before. So this answer, the area in this gray region here, this area is the exact same answer we got before. Now, we just learned that the definite integral is a way of describing area that's below the function c prime of x in this case, between 5 and 10. So we can describe this area here using this notation. It's the integral as x ranges from 5 to 10 of the c prime function, which is negative 15x plus 305 dx. This is area. This is going to be equal to this calculation. And we just established that this is equal to that, which comes from that, which is the c of 10 minus the c of 5. Good. That's what we want to get out of this problem. That, and again, pointing out that the integrand in here, this function here, is c prime of x. So integrating c prime of x from 5 to 10 gives you the exact same answer as evaluating the cost function c at 10 minus evaluating this cost function c, capital C, at 5. Okay, so in two examples, we just noted that this property worked. It was the same kind of concept, they're very similar questions. I just changed the formula. So in both cases, it worked out that both separate equations, both separate calculations resulted in the same value. But that's no accident. It's always going to be true. Okay, so the point of this, the place we want to go to, is to notice that we might be asked to figure out what this is, and that's complicated. It wasn't so bad here because it just turned out that the c prime function happened to be a straight line. Therefore, the area underneath the curvature gave us a shape that we can easily figure out, but even that one wasn't so easy. But we can see that eventually there's going to be equations in here that result in curviness, and then we want to find areas underneath those functions. That's complicated. We could use the approximating rectangle process, but what this does, it says to us that, look, it's easy to figure out. All you have to do is figure out a function whose derivative is equal to this one. So when we start here, we want to go backwards. And once we find that function, all we have to do is evaluate it at the two limits. Okay. Remember that in this process, we went from this function to this function, and going in this direction, we call that taking a derivative. Right? This is find the derivative. But now, if we only started with this one, then going backwards like that is the antiderivative. Okay, so that's where we're heading. We're going to be given some sort of an integral with some sort of an equation in here. We're asked to figure it out, evaluate. It's going to be a definite integral with limits of integration. And the process we want to take advantage of is that if we find an antiderivative, if we can go backwards from here and go backwards and find this equation, then all we have to do is evaluate that equation at the limits of integration, which I think we can all agree was easier than finding that. And then the two answers will match. And that's the fundamental theorem of calculus. Okay, theorem 1, the fundamental theorem of calculus. If f is a continuous function on the set a to b inclusive, and capital F is any antiderivative of f, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. We demonstrated how this works twice already, but we didn't actually prove this. The proof is a little bit beyond the scope of this class, so we're not going to prove it, but hopefully it made sense for the first couple of examples, and we'll continue to do some examples so that we can see how to use it, how to apply it, why we love it. So the fundamental theorem of calculus gives us a way to evaluate a definite integral from a to b of f of x dx easily and exactly whenever we can find an antiderivative capital F of x of lowercase f of x. We simply calculate the difference capital F of b minus capital F of a. If capital G of x is another antiderivative of f of x, then capital G of x is equal to capital F of x plus c, where c is some constant, some real number constant. So when we find the difference, G of b minus G of a, that's going to be equivalent to capital F of b plus c minus capital F of a plus c. And then when we distribute this subtraction sign, we'll see that the c's cancel. The c's will cancel, giving me f of b minus f of a. So in other words, any antiderivative of f of x can be used in the fundamental theorem. One generally chooses the simplest antiderivative by letting c equal to 0, since any other value of c will drop out in computing the difference, f of b minus f of a. Okay, so when we were doing indefinite integrals, it was really important to keep track of or make note to add the c so that we can identify that there's an entire family of functions that satisfy as the antiderivative. But when we're calculating definite integrals, it turns out that the c is not really important because it's just going to subtract off anyway. So there's no real reason to put it in there. Or you can just think of letting c equal to 0. Either way, it won't make a difference. So a little bit on notation. In evaluating the definite integral with the fundamental theorem, it is convenient to use the notation capital F of x and then a bar like this, capital F of x and then a bar and then AB, which represents the change in capital F from x equals to a to x equals to b. That is, this is equivalent to this. And pay attention to the order. The order is important. So here I should just put it together. So capital F of x evaluated from, I'll put a to b is equal to capital F of b minus capital F of a. Okay, so we're integrating from a to b, but then the order comes this way. So this one comes first, and then this one comes second. Okay, so the order is important. All right, let's try an example. Okay, so let's say that we're asked to evaluate the integral from 1 to 3 of the function 3x squared minus 2e to the x plus 3 over x dx. Okay, so let's begin by noting that this is the integrand. So this is our lowercase function f of x. Our goal is going to be to evaluate this integral by first of all finding an antiderivative to this function, capital F of x. And then if we find it, if it exists, then all we have to do is evaluate that function at 3 minus that function at 1. So a little bit of side work. Let's go, well, let's just do it over here. So now finding an antiderivative looked like this, 3x squared minus 2e to the x plus 3 over x dx. So there's no limits of integration. When there's no numbers like this is an indefinite integral. And so this was interpreted as finding the antiderivative. Okay, so to find this antiderivative, let's separate this as 3 integral x squared dx minus 2 integral e to the x dx plus 3 integral 1 over x dx. Luckily, each one of these fits under a simple pattern that we've already worked with. So this will become 3 times, and now this becomes x to the power of 3 divided by 3, right? How do I know that? Derivatives, right? So if we want to go backwards, maybe do a guess and check, bring the 3 out in front, and then subtract 1 from the exponent. That's how we get an x squared. And then the 3 you brought out in front cancels with this 3. So that's how I know that this is going to work out. This is the antiderivative. Minus 2, and then the antiderivative of e to the x is just e to the x, plus 3, and then the antiderivative of 1 over x is ln of absolute value of x, right? We just got to guarantee that this is a positive answer. And then for the antiderivative, there's a whole family of functions, so we have to note that there's a capital C there. Good. So now, of course, this simplifies by canceling that. And so we could say that the antiderivative, which is this thing here, so the antiderivative, we'll call this capital F of x is equal to this, which is equal to that, which is equal to that. So capital F of x equal to that. And capital F of x is equal to x cubed minus 2e to the x plus 3 ln of absolute value of x plus some constant. Now we can identify c could be any real number, right? This is where c equals any real number, where c equals any real number. And the fundamental theorem of calculus says that, well, we could use any antiderivative, any at all. So why not let c equal to 0 and consider one unique antiderivative? So let's switch it up to g of x. So in particular, capital G of x is equal to x cubed minus 2e to the x plus 3 ln of absolute value of x plus 0 is an antiderivative. Is an antiderivative of f of x, our function. Okay, so now according to the fundamental theorem of calculus, now that we found the antiderivative, then it should be pretty easy to come back over here and find this integral. So now that we have that under our belts, so now the integral from 1 to 3 of 3x squared minus 2e to the x plus 3 over x dx, thanks to the fundamental theorem of calculus, this is simply going to be equal to an antiderivative, say g of x, evaluated from 1 to 3. In other words, this integral from 1 to 3 of 3x squared minus 2e to the x plus 3 over x dx is equal to x to the third power minus 2 e to the x power plus 3 ln of absolute value of x evaluated, all of that, evaluated from 1 to 3. Whereas this notation means that we're going to plug in a 3 into all these x's and then subtract a new function where we plug in a 1 into all of these functions. So this is equal to g of 3 minus g of 1. So this would be blank to the third power minus 2 times e to the blank power plus 3 ln of absolute value, of blank. So that'll be all of those guys evaluated at 3. And then I need to subtract minus, and then it'll be all of these guys, same equation, evaluated at 1. So it'll be 1 cubed minus 2e to the blank plus 3 ln of absolute value of blank. Good. So we're going to plug in, the order is really important. So first we're going to plug in the 3 and 3. And then next we're going to plug in the 1, 1, and 1. Right? The order is important. So it's got to be this one first. So we evaluate it right here. And then subtraction. And this is the part that is very tricky. People forget it all the time. We have to subtract the entire thing. So we have to throw in these parentheses and distribute. Otherwise, your whole problem will be off. Okay? So first evaluate it at 3. Then we evaluate it at the 1. So then there's the 1, the 1, the 1. Okay, so now all we have to do is a little bit of arithmetic. We're almost done. So this is going to be 27 minus 2 times e, well, just leave it as 2e cubed, plus 3. Now, we no longer need the absolute values because 3 is positive, right? So I know it's just going to be 3. So that's, you can drop the absolute values. Minus, and now this is going to be positive 1, plus, when I distribute that minus, plus 2e to the power of 1, minus 3 ln, and again, we don't need the absolute values anymore since I know 1 is a positive number. Becomes that. Now luckily, this cancels easily. ln of 1 is 0, so that whole thing just becomes 0. And the rest, well, I can just use my calculator and get an answer from there. And so this becomes approximately equal to negative 5.44. And that's our answer. Okay, so let's pay attention to the process. We're asked to evaluate this integral. And in order to evaluate that integral, thanks to the fundamental theorem of calculus, we know that what we could do is find an antiderivative. So we go back to our work with antiderivatives, which is the reverse of derivatives, right? So we already have some patterns to work with. We know some of the standard ones. We'll develop some more. But we find the antiderivative. The notation for it is very similar to this one, right? The only thing that's different is that here there's no limits of integration. So this one just refers to the antiderivative. There's a whole family of antiderivatives. That's why we put a plus c there. But the fundamental theorem of calculus tells us it doesn't matter. The c's are going to end up getting canceled off anyway. So we can just let g be any antiderivative. So this g is an antiderivative because we know we can always check it. Note that if I take the derivative with respect to x on this g of x function, well, we'll get exactly the f function, the lowercase f function, because it's an antiderivative. That's the definition of an antiderivative. Okay, so once we know that antiderivative, the fundamental theorem of calculus tells us that this integral is going to be the same answer as evaluating the antiderivative at 3 minus the antiderivative at 1, right? This little guy right here. Okay, so now just be careful with plugging it in, and there's your answer. Okay, so now let's use technology to confirm this. Okay, so back to this online graphing tool. I type in my equation into here, and then I want to go from 1 to 3. That was the interval of interest. And then it graphs it. We can confirm that that gray region there is the one we're interested in. Remember that the little area above the x-axis is considered to be positive, so that little area right there is positive. And then the area below the x-axis is considered to be negative. So clearly there's going to be a lot more negative, and that makes sense that our answer is a negative number. And then the computer right here automatically calculates it for us, and it is consistent with the answer that we just got. So this is negative 5.44. Okay, use substitution in an indefinite integral to find the antiderivative and then evaluate this definite integral. Okay, so let's begin by working with an indefinite integral. So that means an antiderivative. We're going to label that as capital F of x. So capital F of x is going to be equal, let me zoom into here. Is going to be equal to the integral of 1 over 2x plus 4 dx. Remember, the difference is here we have limits of integration from 0 to 1. Here there's no limits, therefore this is an antiderivative. Right? This is a definite integral. This is area underneath a curvature kind of stuff. This is an antiderivative. This is just the reverse of taking derivatives. Okay, so let's figure out what this is. To figure out what this is, let's do substitution as suggested. Since we don't really have a standard way of figuring out what this is, it doesn't fit one of our standard patterns. But if we do a substitution where we let u equal to 2x plus 4, then we can replace this 1 over u, and then that's something that we can find an antiderivative for. Okay, however, we have to also replace the dx. So we're going to have to take the derivative with respect to x on both sides of this function. So ddx of the u equals to ddx of the 2x plus 4. So that means that du dx equals to just the number 2. Okay, so then we multiply both sides of the equal sign by this dx, and so we get that the du is going to be equal to 2 dx. du equals to 2 dx. So coming back up to this guy, capital F of x then is equal to the integral of 1 over 2x plus 4 dx. And now I know that I need to introduce an extra term of 2, let's put it in red, so that this whole thing becomes my du. I can't just throw in a 2 though, I got to balance it out, so I'm going to put in a 1/2. 2 times 1/2 becomes 1, and then that doesn't change the value of my result. Okay, so now I'm ready to substitute. This part here, all of it, including the 2, becomes my du. And then in the denominator, I end up getting a u for the denominator. So my new function becomes, so then this then becomes equal to 1/2 integral of 1 over u du. Now, what do I do about this x? I said that this was f of x, but now I've changed it to an f of u, right? Where u is this guy up here, right? So we did a substitution there. Okay, so let's keep working with this, and we know we got to go back, though. We got to change it back to x when we're done. So now this becomes 1/2, and then this is ln of absolute value of u plus c. And so now this is f of u, but we didn't want f of u, we wanted f of x. So we're going to have to change it back and say that f of x must be equal to 1/2 ln of absolute value of, and then the u we said was equal to 2x plus 4, absolute value plus a constant. There's our antiderivative. There, so I found the general antiderivative. And then in particular, if we let c equal to 0, then we can just say let f of x equal to the 1/2 ln of absolute value of 2x plus 4 be the antiderivative, where c, this is where c equals to 0. So if we let c equal to 0, we get to pick any one we want. Why not pick the easiest one? So that just becomes 0. And so now, thanks to the fundamental theorem of calculus, I know that evaluating this really just comes down to figuring out this function. We have to find that function and evaluate it at these two limits. So let me zoom into here. So now I'm ready to answer the original question. So now I know that the integral from 0 to 1 on 1 over 2x plus 4 dx, this integral, is equal to this integral, which is going to be the f of x, capital F of x, evaluated in 0 and 1. Okay. In other words, I could say, well, and then this is going to be the same thing as capital F of 1 minus capital F of 0. Okay. Or, in other words, from 0 to 1, 1 over 2x plus 4 dx is equal to 1/2 ln of absolute value of 2x plus 4, close absolute value, evaluated at from 0 to 1. Okay, so this is going to be equal to 1/2 ln of, and then 2 blank plus 4 blank minus 1/2 ln absolute value of 2 times blank plus 4. Okay, so first we're going to evaluate it at 1. Remember, the order is very important, so we put a 1 first, and then we evaluate it at 0 over here. So this is going to turn out to be equal to 1/2 ln of, and this becomes 2 plus 4 becomes 6. I don't need the absolute values anymore. And then minus 1/2 ln of, and this becomes 4. Okay. So calculating those two things, we end up with 0.203, and that's our answer. Integral from 0 to 1 of 1 over 2x plus 4 dx equals that. Okay, so notice the process. In order to find this integral, in order to evaluate this definite integral, we have to find the antiderivative, capital F of x. We use our techniques from before to find antiderivatives. Once we find the family of antiderivatives, then we can choose any antiderivative. So why not let c equal to 0? And then we found our antiderivative, right? And now, thanks to the fundamental theorem of calculus, finding this integral becomes just as easy as finding the difference of these two values. Evaluate the antiderivative at 1 minus evaluate the antiderivative at 0. Good? So then we can just find them that way. Okay, well, in practice, we usually don't go through the trouble of finding the antiderivative separately and then coming back and plugging it in. It's just a smooth process to just kind of do it all at once. So this is an alternative way of writing down this work, even though it's going to be the exact same thing, the exact same work. So I'm just going to copy it over here. This is the integral from 0 to 1. Okay, so let's say that you wanted to find this integral. First of all, I really wish it became popular for us to identify the 0 and the 1 as values of x. It should be obvious since they all match. This is the derivative with respect to x. This is a function in x. And so these should be values that match that guy. But it would be nice to like really point out that this means that the x is 0 there and that the x is 1 there. Particularly useful when they get more complicated and also when we do things like the substitution rule, which is what I'm going to do right now. So in order to find this integral, what I'm going to first of all do is do the substitution rule. So let's let u equal to the 2x plus 4, just like before. And then I would take a derivative of this guy, so that would be d dx of the u equals to d dx of the 2x plus 4. And so du dx equals to 2. And now du equals to 2 times dx. Okay, so I'm almost ready to substitute it. I'm going to come back over here and I'm going to copy this guy down. And I'm going to let this be x goes from 0, x goes to 1, and then 1 over 2x plus 4, and then the dx. Okay, so just like before, we noticed that I need an extra 2. So I'm going to throw in a 2 right in there. That way that's my du. And I need to balance it out with a 1/2 out here because I can't just throw in a 2. So I got to balance it out. 2 times a half is 1, and 1 times anything doesn't change the value of our equation. So now I'm ready to substitute. So the way I'm going to substitute it is by noting that this whole thing in here is going to be my new du, and that this thing here is going to be my u. So I'm going to write it down as the integral. There's going to be a 1/2 out here, and it's going to be 1 over u du. And now notice that I want to change the limits of integration as well. These are associated with the x, not associated with the u. So you got a couple of options. Option number 1 is to keep track of it like this. Let x equal to 0, x equal to 1. We know that the next step then is going to be to recognize that the antiderivative of this thing is just going to be to have 1 over ln of x. So this becomes 1/2 ln of absolute value of u. And then we know that we want to evaluate this as x goes from 0, x goes to 1. Now, I keep track of these, let me highlight them. I keep track of these x's here because this function is in u, so we can't plug in a u in there, right? So it would be wrong to say that it's ln of 1 minus ln of 0. That's not true because this is a u function. Good? So now what we could do is come back and substitute my u and say that this is going to be 1/2 ln of absolute value of, and now my u is 2x plus 4. And now I can say, let's evaluate it at 0, evaluate it at 1. So then this becomes 1/2 ln absolute value of 2, and then that's where the 1 comes in, plus 4 minus 1/2 ln of 2 blank, that's where the 0 comes in, like that. And so we either plug in a 1 from here or a 0 over here. And we still end up with our answer of 1/2 ln of 6 minus 1/2 ln of 4. So we get the same result as before. Okay, option 2. At this stage, though, what we could do is, at this stage here, so this is option 1, option number 1. On the other hand, the other option would be to go from this point and go over here. I'm going to copy it down again. So let's copy this down exactly the way it was. So let's go over here. There's an integral. X goes from 0 to x goes to 1. And then we have the 1 over 2x plus 4. And then dx. And then we put in a 2 there, put in 1/2 there. Okay. So the option 2, the next option is going to be to say, copy this guy again. So there's a 1/2 there, integral there, 1 over u there, du there. But then what we could do is transform the limits of integration. So I can say when x equals to 0, what is u going to be? U, well, u is defined right here. U is going to be equal to 2 times blank plus 4. And that blank would be a 0. So u becomes 4. So instead of x goes to 0, then it changes into a u equals to 4. Good. And also, when x equals to 1, u goes to 2 times blank plus 4, and that blank is going to be a 1, so u equals 6. So now this becomes u equals to 6. And now they all match. The limits of integration match the variable of of integration. And the function is written in the same variable. Everything is u. So now we can evaluate this. So just like before, we see that the answer is just going to be equal to 1/2 ln of absolute value of u. And now it's evaluated as u ranges from 4 to 6, and now we can just plug them in. So this becomes 1/2 ln of 6 minus 1/2 ln of 4. Right? So we get the exact same answer every time. This answer matches this answer, and they both match the other one. So let me zoom out. Okay, so we could go off to the side and find the antiderivative function and then come back and use the fundamental theorem of calculus to find our result. Or we could do it in one of these two ways where we're kind of blending it all in one. So in this method, we use the u substitution. We keep our limits of integration in the variable x. So then we find our antiderivative in terms of u, and then we have to resubstitute u back in terms of x so that we can evaluate our function with respect to x. Right? So just be careful that if you do a u substitution and you don't change the limits, you can't just plug in x equals to 1 into here. Okay? On the other hand, what we could do is go off to the side and figure out how the new substitution of u gets affected by the limits of integration. So you can change the limits of integration into the variable u. So now we can figure out when x equals to 0, we get a u of 4. When x equals to 1, we get a u of 6. So we can do a complete transformation of the variables So we changed the dx into a du. We changed the equation into something that involves a u. And we also changed the limits of integration to involve the variable u. Everything matches. So we don't have to go back to x anymore. So we find the antiderivative, and then we just evaluate it, and we end up getting the same answer. Oh, so let me separate this here, and then let's put this like this. So this is option 2. So 3 different ways of doing this. Find the antiderivative first, kind of separately, find that answer, come back, and then evaluate it this way. So this is one way of doing it. Second way of doing it is to kind of blend it a little bit, do the u substitution, keep your limits of integration in the original variable x, then find the antiderivative, and then resubstitute u back into x, and then you'll get your answer. That's option 2. Or well, option 1 here, and then separate from that one. And then the next one is to do a substitution of u, but also substitute the limit. So it's like a complete substitution, a complete transformation of a brand new integral that has no more x's in either the equation, the variable of integration, or even the limits. And then you don't have to do a resubstitution when you're done with your antiderivative here. And then that will also lead to the same answer. Okay, so 3 different ways of doing this. No, you do not have to do it in every single way unless you're specifically asked to do so for some reason, but I doubt that would happen. I'm just illustrating for you the 3 different ways that we can do this. Pick your favorite, whichever one makes most sense to you, and stick to it. And try not to get confused between one method or another. Or if you see a solution worked out for you somewhere, it might be worked out in one method or another, so you should see or you should know that there are connections between them. Okay, so we can also use technology to confirm our work. Typing in 1 divided by, and I'm going to make sure to put parentheses there to include the entire denominator. That would be 2x plus 4, close parentheses. We get that, and we want to go from 0 to 1, from 0 to 1, and then let's zoom into here. So this is the area underneath the function that we're interested in, and as you can see here, we get an answer of 0.202916, which is equal or close to the 0.203 that we found. So as an exact answer, we found the exact answer, and then we can use our calculator to approximate it, and we got pretty much this right here. Okay, so this function here, this is the function 1 over 2x plus 4, that was f of x, equals to this, and that would be this function here. And we just discovered that this gray zone here is equal to this. So this whole area here is 0.203 as an approximation, or this as an exact answer. So that area is this right here, which we also identify with this notation, right? So the integral between 0 to 1 on this function is exactly what we were asked to find. The integral from 0 to 1 on 1 over 2x plus 4 dx, which is this area in gray, and we established that it equals to this. Okay, moving on to another example. Okay, a management service found that maintenance costs, dollars per year, increased at a rate of m prime of x equal to 90 x squared plus 5,000, where m of x is the total accumulated cost of maintenance for x number of years. Okay, so write a definite integral that represents the total maintenance costs from the end of the 2nd year to the end of the 7th year, and evaluate that integral. Okay, so this is clearly going to be equal to the integral from the end of the 2nd year to the end of the 7th year. So that would be from 2 to 7 on this, which would be equal to 90x squared plus 5,000. dx. So here is our definite integral. And then to evaluate it, we need to find the antiderivative. So this is going to be easy. This is going to be equal to something about x to the third power, right? Because its derivative subtracts 1. That's how I know that I need an x cubed, because there's an x squared there. But then I need to divide it by that guy, because when I bring down the 3, I want it to disappear. So I'm going to do 1/3 x to the third. That's my general rule. And then I have a 90 still there, plus, and then 5,000 x, and then that gets evaluated from 2 to 7. Of course, this can be reduced a little bit. This becomes equal to 30 x to the third power plus 5,000 x evaluated from 2 to 7. So this becomes 30 blank cubed plus 5,000 blank minus 30 blank cubed plus 5,000 blank. Now be real careful to make sure to wrap these around parentheses. So that'll be this equation right here. There's a plus sign, minus, and then this equation over here, and then that minus sign gets distributed. So the first one is going to have a, well, let's put it in green. First one's going to be a 7, right? We always start from the top one. Evaluated at 7 minus evaluated at 2. The order is very important, so make sure you're consistent with your work. Okay, and now all we have to do is get our calculator and figure out what that is. So after a little bit of calculator work, we'll see that this is equal to, this one's equal to 45,290 minus, this one's equal to 15,810, and so together they give you 29,480. Okay, so copying this integral down, we say the integral from 2 to 7 of 90x squared plus 5,000 dx equals that, right? So on the left-hand side, this is the same. This integral equals that. This integral equals that. Okay, so I'm just being lazy here. Same, and then we can box this up as our answer. So write a definite integral that represents the total maintenance costs. So the total maintenance costs from the end of the second year to the end of the 7th year equal $29,480. Okay, definition of average value. So the average value of a continuous function f over the interval from a to b is equal to 1 over b minus a integral from a to b of f of x dx. So it's just our standard integral, and then we divide it by this quantity b minus a. Okay, let's do an example. So, for example, find the average value of f of x equal to 6x squared minus 2x over the interval from -3 to +2. Okay, so using our formula, we get that the average is going to be equal to 1 over b minus a integral from a to b on f of x dx. Zoom into here a little bit, a to b. Okay, so then the average value of f of x is going to be equal to 1 over b, which in this case is a 2 minus -3, integral from -3 all the way up to 2 of my function f of x, which was 6x squared minus 2x dx. Okay, so then this simplifies to 1 over minus minus, so that just becomes plus 5, so that's 1 over 5, integral from -3 to 2 of 6x squared minus 2x dx. So now we need to find an antiderivative for this guy. That's going to be easy. That's going to be 1/5 times, and now let's leave the 6 alone, And then I know it has something to do with an x to the third power because its derivative brings it down to 2. So we also have to get rid of that 3. We multiply it by 1/3 minus 2, and then x to the power of 2, and then 1/2. Right? So then guessing and checking, we see that that is the antiderivative. And then this gets evaluated as x goes from -3 to +2. Of course, this reduces a little bit. These two cancel, and this goes into there twice. So we get that this is equal to 1/5 2x cubed minus x squared, evaluated from -3 to 2. And so now this is equal to 1/5, and then 2 blank cubed minus blank squared minus 2 blank cubed minus blank squared. And let's be careful to put parentheses around here, parentheses around there, and also a giant bracket here to indicate that the entire thing is being multiplied by this 1/5. The 1/5 applies to all of it. Okay, so now I'm going to put in a 2 into this equation, and then I'm going to plug in a -3 into this equation. Okay, so now evaluating this, we get 1/5 giant bracket. This is going to be 2 to the third power. That's going to be an 8 times 2 makes it 16 minus 4 minus, so that's these guys here. Now -3 to the third power, that's going to be -27 times 2 makes it -54. So this would be -54 minus, and then -3 squared becomes +9. So we get this and we get that in a giant bracket. Okay. So then this becomes 1/5 times, and then 16 minus 4 is going to be 12. Minus becomes +54. Minus becomes +9. So 12 plus 54 becomes 66. 75. Get 1/5 times 75, which then becomes 15. Okay, so bringing it all together, I'd say that the average value was equal to this one integral, which is equal to 1 over 2 minus -3 integral from -3 to 2 on 6x squared minus 2x dx. So that gives me my average value. And after a lot of work, we found that that answer was equal to 15. Okay, my average value equals to this integral, and we solved it. We got an answer of 15. Okay, so one last example. Given the supply equation, P equals to S of x equal to 10e to the power of 0.05x, find the average price in dollars over the supply interval from 25 to 35. Okay, so average price, so the average price in this case is going to be equal to, okay, we need a fraction out here, it's b minus a integral from a to b on my function f of x dx. Well, in this case, it's going to be the s of x. Let's change this. It's going to be some function s of x dx. Okay, so that means that that average price is going to be equal to 1 over, and this is going to go from 35 to 25, integral from 25 to 35 on my function 10e to the 0.05x dx. Okay, so how do we simplify that? Okay, first of all, this becomes just 1 over 10, integral from 25 to 35, and this becomes 10e to the 0.05x dx. Luckily, this 10 and that 10 cancel, so that's an easy cancellation right there. And we can simplify this a little bit and say that this is then just equal to the integral from 25 to 35 on the function e to the 0.05x dx. Okay, to simplify that, we're going to do a u substitution. Let's let u equal to 0.05x, and then the derivative with respect to x, d dx of the u equals to 0.05. Oops. I meant to write down the d dx on the 0.05x becomes du dx equals to 0.005. Multiplying both sides by the dx, we get that the du equals to 0.005. Wait, why are there two zeros? 1 0. 0.0505 dx. Okay, so looking at this guy here, it almost looks like I'm ready to substitute it, but I do need to introduce that extra 0.05, which means this has to be 1 over 0.05. Good. These two kind of balance each other out. This fraction times that decimal become 1. They cancel out, so I haven't changed anything. But this lets me substitute my u value right here. This becomes my du. Okay. What about the limits of integration here? Well, I'm going to keep them as an x. So I'm going to keep track of this by coming back over here and noting that this is x goes from 25 and x goes up to 35. Now I'm ready for my substitution. So I'm going to say that this is equal to the integral from, there's a fraction out here, 0.5, integral as x ranges from 25 to x goes up to 35. And then this becomes e to the power of u. Right, that was the whole point, that this whole numerator there can become u, du. Du. Good, so this whole thing becomes du. That becomes e to the u. And that is great because now this antiderivative is really easy, right? We know that the antiderivative of e to the u is just e to the u. So let me zoom out. So now I can take this over here and say that the average price is equal to 1 over 0.05 and then integral of e to the u du, and let's not lose track of the fact that this is a 25 here. X goes from 25 to x goes to 35. And now I can find that antiderivative. So let me zoom into here now. That means that this average price becomes 1 over 0.05. The antiderivative of this is just going to be e to the u, evaluated as x goes from 25 to x goes to 35. This times that. Good. And now I'm going to resubstitute my u. This becomes 0.05 e to the power of, and we let u equal to, coming back over here, u was equal to this decimal, 0.05 x. So remember, u was equal to 0.05x, and that's what gets plugged right into here, 0.05x. And then we're evaluating this as x goes from 25 to x goes to 35. And so we're almost done. This becomes 1 over 0.05 e to the 0.05 times 35. Well, I'll leave a clear color blank minus 1 over 0.05 e to the 0.05 blank. So here we're going to evaluate this at 35, and here we're going to evaluate this at 25. Okay, we've gone as far as we can go without the use of a calculator, so then we just grab our trusty calculator and write down our answer. So this was average value, the average price, in this case, the average price, was equal to the integral from, setting up the formula from up here. Average price was 1 over 35 minus 25 integral from 25 to 35 on the function 10 e to the 0.05x dx. And we see that it equals to this. And if we simplify that a little bit, we'll get that this equals to 45.29. Okay, and that's our answer. Zoom out. Okay, so hopefully this should be more than enough material to get you started on your homework. Please stop by my office hours if you have any questions.